Okay, let's get started. Okay. So before starting today's class, I will announce about the midterm statistics. So as you know, I believe everyone knows. So we will take the midterm exam on Thursday. Okay. So then next tomorrow. So and then this is the close to book exam, and then this exam will cover until we learn today's class. Okay, so then actually we will take the exam during the regular class time, which means that the exam will exactly start at 10:30. Okay, and then I believe the exam will end at 12. Okay, so it will take 1.5 hours. I think it's okay, right? Are you okay? And then, this exam is the closed exam, so you cannot wait, you cannot see any reference book, so you cannot use any electric devices except the simple calculator. So, the exam will include some questions that require calculation, right? So, but actually in chapter 1, we learned about the performance metrics. So, and then not to compare the performance of the two systems, we need to calculate some. So we need to compute some the instruction count and then the CPI and clock period, right? So you may require simple calculator during the exam. And then, so actually we will prepare the extra calculators, but but it will be better if you prepare the calculators, right? Okay, and then I believe the difficulty level of the exam will be similar to the difficulty level of the homework questions. Okay, okay, and that's it. Any questions? Okay. So, in the previous class, we learned about the data path of the single cycle processor. Okay. So data path means that data paths include some hardware component which calculate the which store some data, also which performs the arithmetic or logical operation such as the add, subtract, and which means that if hardware, actually the computer hardware performs the data processing. So which means that the data are read from the memory, and then these data can be processed by hardware like the ALU, arithmetic logical unit, and then the computed results are stored to the memory or register file. So the hardware component that is required, those they are required for these operations, and then also the data path, the connections between the hardware component for the data path. So which means that data path includes the hardware component, then the connections between hardware components. Okay, so in the previous class, we learned about some detailed operation of the hardware component and the data path. So we learned about the instruction memory, and then register file, ALU, and immediate generator here. And then also we learned about the data memory. Okay. So as you can see, so in order to support some different types of instructions, then our single cycle processor includes the multiplexer. So actually, I also explained about the multiplexer. So multiplexer has multiple inputs like A and B, and then the outputs are connected to one of these inputs by selection signal. Okay, so this is the function of the multiplexer. So as you can see, our single cycle processor includes the multiple multiplexers here and here and here. And so you need to remember the 5 required steps for executing instructions. So which is very important. Okay. So the 5 required steps are: the first, instruction fetch, instruction decoding, and execution, memory, write back. Okay. And also you need to remember which operations are performed by each step. Okay. So what is the instruction fetch? So in the instruction fetch step, the instruction, the inst is read from instruction memory. Okay. So fetch, what is fetch? So fetch means that some instructions are delivered from one place to other place. And then I also mentioned that the processor reads the instruction from the memory. So this process, this operation is called instruction fetch. So instruction fetch means that the instruction is read from instruction memory, and the instruction decoding. So the instruction given to a processor are encoded. So it means that actually I also explained that the computer is the kind of digital system, and digital systems can only understand the digital signals, electric signals, and then these electric signals have includes only 1 and 0. So actually the instruction need to be encoded, so which means that the encoded instructions are analyzed by a processor, and then processor need to recognize the type of instruction, and then register numbers or some operations, the required operations by instruction. And during the instruction decoding step, a certain instruction reads the operands from register 5. Okay. So for example, alpha instruction, also load instruction, actually every instruction, so most instruction needs to be operand from register 5. The instruction decoding step also includes is operand read and execution. Each instruction requires some operation like the add, subtract, multiply, or exclusive, or something like that. So actually during the execution step, the processor performs the required operations. Okay, for each instruction. And then during the memory step, and then I also explained that some instructions such as the load and store instructions required to access data memory. So the memory step is required for load and store instructions. Okay, load word or store word instructions. So which means that the data memory is accessed by a processor. And write back. So write back means that the many instructions, the result should be written back to the register file, right? So write back equals the write back of a result to the register file. Okay. So these are the 5 steps done by a single cycle processor, and then not support these operations. So we have some hardware components such as memory, register file, ALU, and then these hardware components have input and output ports. So it's like the black box. So which means that if some input data are given to this black box, and then this black box generates the output result. So you can see that these hardware components look like the black box actually, the box. So the input data are given to this hardware component, and then as you can see, the output data are generated. Okay, so which means that hardware components have input and output ports, and then so we need to connect the input and output ports of each hardware component. So we can build the data path of the single cycle processor like this figure. Okay. So in this figure, you can find that some hardware components here, and then also you can find some connections like here. So you can find the data connections. Okay. So for example, if you see the data connections between instruction memory and register file, then you can find that instruction which we can generate, not generate, we can read instructions from instruction memory. So this is the output of instruction memory, so instructions, and then how this instruction is delivered to other components. So we can find some line connections. So we can find that. So this instruction is given to the register file, like the read register number 1, read register number 2, and write register number 5. So we already know that only some fields are delivered to the register file, right? And then also this instruction is delivered to the immediate generator. So which means that if we see this figure, the diagram of the data path element, then we can find that how data are connected from one hardware component to the other hardware component. Okay. Okay. So we can build the data path of the RISC-V single cycle processor like this. And then what is missing? So if you see this figure, then you can find that all input and output ports of hardware components are connected, but which ports are not connected? Right? AU source, AU operation, PC source, am I right? Yes. So you can find that for these hardware components, these ports are not connected. And then why? These ports are control ports. So which means that control signals are connected to these ports of the hardware component. So what are control signals? Control signals decide behaviors of target hardware component, right? So, for example, if we see this multiplexer here, so we can find that the ALU source is the control signal of this multiplexer, and then by the result of this ALU source, the behavior of a multiplexer is determined, right? What is the behavior of this multiplexer by ALU source? If the ALU source is 0, then the output of a multiplexer is connected to this path, the I0, the first input. And if the ALU source is 1, then this port is connected to the output port of this multiplexer, right? So control signal decide the behavior of target hardware component. So, and then in this figure, that we can find that control signals are not connected. So it means that in this class, so we will learn how to generate control signals for single cycle processor, right? Okay, so we will learn about the control signal. So what is different? So in this figure, then we can find that this unit is newly included, right? So this unit is called the control unit. So you can find that this the name of the unit is the control. So this is the control unit. And then as you can see, so this control unit receives instruction from the instruction memory. So you can find the connection here. And then this control unit generates many control signals. So these control signals are connected to the control ports of many different audio components, right? So in this class, we will learn how to build this control unit, okay? And how to generate the control signals from the instruction, okay? So as you can see, the only instructions are connected to the control unit. So which means that the input of this control unit is the instruction, and the output signals are control signals. Okay. So let's focus on the ALU operation. Okay, here. So why? So firstly, we will focus on the ALU operation because the this ALU is used for many instructions. So which means that we can use the ALU for the arithmetic or logical instruction like add, subtract, exclusive or and. Also, we can use this ALU for other instructions, such as we can use the ALU for memory instruction. It is because ALU can generate the address for the data memory. So you can find that the output of ALU is connected to the input of data memory, and then this is the address. So which means that ALU can be used for calculating addresses for load and store instructions, right? Also, we can use ALU for the branch instructions like BQ. Okay, so BQ X1 and X2, and then in order to compare these two different components, then we need to perform subtraction like X1 minus X2. Right? In order to check the equality, we can perform subtraction. So which means that this ALU can be used for the branch instruction. So ALU can be used for different kinds of instructions. So which means that the behavior of ALU is to be controlled by control signals called the ALU operation. Okay. And then this ALU operation is also generated by control unit based on the instructions. Okay, let's see which operation is required for ALU. As I explained, the ALU is required for load and store instructions. And then if we see the load instruction like load word X1 and then X2 and immediate, then actually, in order to calculate the address of the load instruction, then it performs the X2 plus immediate, right? So which means that for the load and store instructions, ALU needs to perform add operations. Okay, so required operation is the add. And then for the branch instruction, actually, I explained that this single cycle processor supports the only BEQ, like the BEQ, BEQ X1, X2, and target. So, which means that we need to perform the X1 minus X2, which means ALU needs to support subtraction of branch instruction. And then for other arithmetic or logical instructions, ALU needs to support some different kinds of operations. So you can find the required operations by ALU for the different R-type instructions. So ALU needs to perform AND or add or subtract instruction. And then in order to support the AND or add and sub instruction of this 5, right? And then these are the ALU control signals. So which means that if ALU receives ALU control signal which is equivalent to 0, 0, 0, 0, then this ALU performs AND operation. Okay, so which means that if a processor is executing AND instruction, then ALU control bit should be set as 0, 0, 0, 0, right? Okay, in order to support the AND instruction. Okay, then but in this single cycle processor, then the ALU control signals are decided by 2 steps, like the, and first with the different OP code field, actually the control unit check the OP code field of the instruction, and then the control unit decides the ALU OP signal, ALU operation signal. So this is the 2-bit signal, okay? So 2-bit ALU OP signal, and then this ALU OP signal is determined by category of instruction, right? So for example, if the instruction is the load instruction or store instruction, then ALU OP becomes the 0, 0, okay? So in this case, ALU performs the only add instruction. And then if the OP code field is the write instruction, like EQ, then ALU OP becomes the 0, 1. So which operation is required? Subtract operation is set for the ALU. Okay, so in this case, the ALU control this bit, it becomes the for the memory instruction, ALU control signals are always 0, 0, 1, 0, which means it's the add operation. And if the instruction type is the write instruction, then ALU OP becomes the 0, 1, and ALU always performs subtract function. Okay, in this case, ALU control bit becomes the 0, 1, 1, 0. Okay, here, and then if the given instruction is an archive instruction, then ALU OP becomes the 1, 0, right? And then if the given instruction is an archive instruction, then also the ALU operation is determined by other fields like the function 3 field or function 7 field. Okay, and then based on the other function 3 or function 7 field, the ALU function is also decided like add, subtract, and or. Okay, so let's see some connections of the ALU operation. Okay, so if you see the control unit here, so you can find the control unit here. Okay, so and then as you can see, for this control unit, only the instructions are given to this control unit, but you can find that instruction 6 down to 0 are given to the this control unit. Why? So what is the instruction 6 down to 0? This is the OP code field, right? In chapter 2, we learned that the instruction bit 6 down to 0, the LSB 7 bits are used as the OP code field, right? And this OP code field besides the category of instructions. Like so for example, so if you see this OP code field, so you can find that based on the OP code field, we can know the category of instruction, category of instruction, right? So based on the OP code field, then control unit will figure out which type of instructions are given to its processor. Okay, then ALOP, these 2-bit control signals are determined by OP code field of an instruction, and then this ALOP signal is given to the ALU control unit. Okay, so if you see the input of ALU control unit, there are two inputs. The one input is the ALU OP, so it's from the control unit, and then the another input is the instruction. So actually the ALU control signal receives the function 7 and function 3 fields from the instruction, right? So it is because if we see the this table, you can find that many arithmetic and logical instructions have the same OP code field. Okay, and then the instruction is determined by function 3 and then function 7 field for the R type instruction. So in order to determine the operation of the ALU for the arithmetic or logical instruction, this ALU control needs to receive function 7 or function 3 field of one instruction. Then the final control signal for the ALU is determined. Okay, it's determined. So ALU control signals can be generated like this. But then actually, if you can understand this RISC-V instruction format, then you can easily determine which control signals are required for the target instruction. Okay. So just remember that in this figure, the ALOP, firstly, the 2-bit ALOP control signals are determined by OP code field of an instruction, and then the ALU control signals are determined by either function 3 or function 7 field for the R type instruction. But if the OP code field, actually the ALOP is the 00 or 01, then ALU function is determined regardless of the function 3 or function 7 fields. Okay. Okay, this is the ALU control signal, and then I actually this slide also explains how the ALU operations are decided. Okay, and then let's see the other control signals. For example, and then if you see this control unit, then you can find that the control unit generates many other control signals. So you can find the branch is here, mem read and mem to register, and some other control signals are also generated from control unit. And then also you can find that only OP code field is given to this control unit. So which means that these control signals can be determined by monitoring OP code field of the instruction. And then let's see how these control signals are determined. Okay. So let's see the R type instruction, right? The add R type instruction is the add x1, x2, x3. And then let's see how this R type instruction is determined. So during the instruction fetch stage, fetch step, the instruction is read from the instruction memory. So this is the instruction fetch step. And then, as you can see, this read instruction is given to the control unit. So you can find the OP code field. Also, the other fields like the RS1, RS2, then RD are given to registers, and then also some other fields like the function 3 or function 7 fields are given to the ALU control unit. So, but which operation is required, like add x1, x2, x3? So in order to execute this add instruction, so we need to read the two operands from register file, right? And then these read operands are given to ALU. Okay. So first, so you can find the read data 1 and the read data 2 port, right? So these two ports are output ports of the register file. So read data 1 is directly connected to the ALU. But if we see the read data 2 output from the register file, so we can find this read data 2 signal is connected to the one of the inputs of is multiplexer, the box. And then, which means that for this, okay, so for this instruction, the control unit need to decide this control signal, right? ALU source. What is the value of ALU source for the R5 instruction? What is the value of ALU source? H. So this is 0, as you can see, this is 0 and this is 1. So what is the value of ALU source for the R5 instruction? H 0. Okay. So if you see this figure, then you can find that in order to perform the add x1, x2, x3, then these two operands are read from the register file, then is need to be connected to the ALU. And then in order to connect this input to the output of a multiplexer, this ALU source need to be 0. So you can find 0 here and 1 is here. So which means that for the R-type instruction, ALU source should be 0. Should be set as 0. Okay, ALU source is 0. And then you can find the other control signal. Actually, ALU OP is the 1, 0. Okay, so it's the R-type instruction. And how about the memory control signals? You can find the mem write or mem read. What is the value of this mem read or mem write? So in the control signal, usually, it's usually, not always, but if the control signal is 1, so which means that it's enabled. And if the control signal is 0, which means that it's disabled. Right? Usually, but actually, our processor design use this convention. So let's focus on the data memory. So for the R-type instruction, what are the values of memory read or memory write? So first, you need to know that the R-type instruction does not access data memory, right? Which means R-type instruction does not use data memory, which means this instruction does not need to read or write data memory. which is mem read need to be the value of the mem read is 0, right? Because it's nothing. And then mem write is also 0. Okay. So this is a 0, and then this is also 0. Then it's just simple, right? And then how about also you can find that for this multiplexer, the selection control signal mem to red is connected. Okay. So what is the value? So you can find that if this selection signal is 1, then for this output of the multiplexer, the memory output is connected. And then if this value is 0, then you can find that the result from the ALU is connected. So if the current instruction is arithmetic or logical instruction, which input need to be activated? So actually, this is the R-type instruction. So we need to store the result from ALU, right? So the output of this multiplexer needs to be connected to this input, right? So you can find that this is the 0. If the selection signal is 0, this input is selected. And then selection signal is 1, this input is selected. Then, what is the value of mem to red for the arithmetic instruction? So we need to connect this path for this multiplexer, so which means mem to red should be 0. So you can find that this is 0, right? So this is 0. And then how about, and then range? So it's simple. So you mean this branch is connected to this AND gate. This is the AND gate. And then also another input of this AND gate is connected to the 0. But it's simple. So it means that this control signal indicates that the first instruction is the branch instruction. So it means if the R-type instruction, like add x1, x2, x3, is the current instruction, then this branch control signal becomes 0, right? So simple, right? Okay. So we determine these all control signals except the red write. So you can find that red write is connected to this control signal port of the register file. So what is the required operation of this add instruction? So finally, the result of add instruction is written back to the destination register, which means that this instruction requires write back to register file. So which means leg write should be 1, because this instruction requires register write. So we can decide all control signals based on the instruction types. So if this instruction is the R-type instruction, the control signals are determined like if the branch is 0, mem to read is 0, mem to read, mem read is 0, and the mem to register is 0, ALOP is 1, 0, and then regular is 1. Okay, it's simple, right? Then how about the load instruction? So what is the example of load instruction? So it's the load x1, x2, and immediate. Okay. So during the instruction fetch step, the instruction is read from the instruction memory, and then also you can find that the opcode field is connected to the control signal. So what is the opcode field of the load instruction? This is the is 1. 0, 0, 0, 0, 0, 1, 1. Okay? Okay. If the current instruction is the load instruction, what is the branch? Branch is 0, right? Because this is not a branch instruction. And then if we see that this ALU source, then actually the load instruction needs performs the X2 plus immediate. So which means that actually RS1 plus immediate. So this is the output of the RS1. So if we can find that the one of the input of the register 5 is directly connected to the ALU, but we can find that the second input of the ALU is connected from the multiplexer. And then, for the load instruction, we need to perform RS1 plus immediate. So which means that for the second input, this instruction needs immediate data from immediate generator, right? So you can find that this is the immediate generator. So the output of immediate generator is connected to the one of the input of this multiplexer. So if the current instruction is the load instruction, then we need to activate this path. So which means ALU source becomes, so this is the 0 and this is 1. So ALU source control signal becomes 1, right? H1. So this path is activated to the ALU. And as the load instruction accesses data memory, and then the load instruction reads data from the data memory. So which means that memory is the 1, right? Because we require read operation from data memory, right? And then how about the mem write? Does the load instruction store data to data memory? No. So actually, memory write operation is not required. So memory write is 0, right? And then how about the mem to read? So what is the operation of the load instruction? The data is read from the data memory. Then this read data is written back to the register file. So you can find this multiplexer. And actually, the output of this multiplexer is connected to the right data port of the register file, right? And then for the load instruction, the data from data memory is written back to the register file. So which means that this path, the output of the data memory needs to be connected to the output of this multiplexer. So which means that you can find that this control signal is the mem to read, so which means this control signal becomes the 1 for the load instruction, right? It's simple. But actually, as I explained, if the control signal is 1, this switch means enable, and then the mem to read is the control signal names the memory to register 5, so which means that if this control signal is 1, which means the output from memory is written back to the register file. And how about the ALUOP? ALUOP is the 0, 0 as we learned. And then the last, regular. What is the value of the regular? So if we know the definition of the load instruction, then we can know that load instruction includes destination register, and then load instruction stores the load instruction right back the data from data memory to the register file. So which means that load instruction requires register write, right? So which means this is the one, because load instruction needs to store some data to the destination register file, right? Okay. 네. 그건 아니고요. 이 스텝장인데, the opicode field is the second bit from this opicode field. So many control signals are generated. So actually the input and the bit resolution of the input and output, there is no relation. So there is actually from the input signal, we can generate the many control signals. Okay? 그러니까는 사실 input하고 output에 그 control gain signal은 사실 관련이 있어요. So there is no relation between the bit resolution of input signal and then bit resolution of output control signal. So in this example, the bit resolution, the number of bits for the output signal is 8. So we can generate many other control signals, right? So actually it can be, so this is a very simple process of design. So we can have only very small number of control signals for real control. Real processor has real processor have many other control signals. Okay? Is the second bit, we can generate many other bits for the control signal. Okay. Okay, so the load instruction like this. Then, there is no. If the current instruction is the store instruction, like the store x1, x2, and immediate, what is different? If the current instruction is, so actually we see the control, we check the control signals of the load instruction, but if the current instruction is the store instruction, then what is different? So actually so for the store instruction, so if you see the also, if you know the definition of store instruction, we can easily determine the control signals of store instruction. The branch is 0 because it's not a branch instruction, and then mem read is 0 because it's store instruction. So actually for the store instruction, the memory is not read. So actually the data is stored to the data memory. So memory read is 0. And how about the mem to read? Store instruction does not have RD, right? Because the destination of store instruction is the data memory, not register file. So actually don't care. So it can be 0 or it can be 1, but no problem. So it's don't care. So which means it can be, so control signals can generate 1 or 0 for this meant to read control signal, but it's okay. So no problem for the store instruction. So don't care. It can be 1 or 0. And then ALOP is the 00 because this is the memory instruction. How about the mem write? Mem write is 1 because the data is stored to the data memory for the store instruction. And then ALU source is also 1 because we need to use the immediate data. Right? How about read? Read write. So store instruction does not require register write. right? So reg write should be 0. Okay, because the store instruction has only rs1, rs1 and rs2. Okay, so the store instruction. Then how about the branch instruction? So the branch instruction, so this object code field of the branch instruction is equivalent to the control. And actually, when the branch instruction is true, then if we see that this multiplexer, if we see that this multiplexer, then we can find that the one of the input of this multiplexer is connected to the this adder, and then what is this adder? So what is the output of this adder? It's the, so this is the PC, and then this is the adder. So this is the PC plus 4. Okay. So one of the input of this multiplexer is the current PC plus 4. And then another input is the, also this is the adder, and then also the one of the input of this adder is the shift left 1, and then it's the immediate generator. So which means that this is the immediate it's immediate shift left 1. Okay, and then the another input for this adder is the PC. So the output of this adder is the current PC plus immediate left 1. Okay, so which means this is the target of branch instruction. Okay, so what does that mean? Based on the condition of the branch instruction, the next program counter value can be PC plus 4, that is the false for the branch instruction, or PC plus immediate multiplied by 2 for the true of branch instruction. Okay, so you can find that the selection port of this multiplexer is connected to this adder. Okay, so you can, so which means and then you can find the one of the input for this adder is connected to the branch control signal here. Oops. Branch control signal. Also, the another input of this adder is connected to the 0 detection from ALU. So which means that so we already know that the ALU OP signal for the branch instruction is 0, 1. So in this case, the ALU performs the RS1 minus RS2. And then what also for this is the BQ instruction, then we need to check the equality of the branch instruction. So RS1 minus RS2 is performed, and then this is the result of the ALU. And if the result is 0, then this zero detection bit becomes the 1. Okay, if the result of ALU is 0. Okay, so what does that mean? So it's a PQ, and then PQ x1, x2, and then for this PQ, the subtraction is performed. So and then if the 0 becomes the 1, this is the true. The condition of the branch instruction is true. So PQ condition is true, then it becomes 1. And then this is the branch instruction. So which means that the branch control signal is 1. And then this is the AND gate. So if this is the one and this is one, then output of the AND gate is one, which means for this multiplexer, this input is activated. So for the next PC plus immediate multiplied by 2 is connected for the next PC. So this is the operation of the branch instruction. Okay. So this line is connected to the next PC of the is processor. So do you understand? So if the branch is the current instruction is branch instruction, then branch becomes one. So which means that one of this AND gate is activated, and then this another input of the AND gate is connected to the ALU, the zero detection bit. And then which means that if the branch condition is true, then 0 becomes 1 for the BQ because this is the BQ. Then this 0 becomes the 1, then this selection signal becomes 1. So in this case, the target of the branch instruction becomes the next PC. And then if the branch condition is false, which means that if the subtraction is performed, then the result is not 0, which means it becomes the 0. So in this case, if the one of input of the AND gate becomes 0, so it becomes 0. So which means that the next PC becomes the PC plus 4, right? That's how the branch instruction is working in the single cycle processor. Then how about the mem to read? Mem read. So the branch instruction does not access data memory, so which means mem read is 0. And how about the mem to read? The target of the branch instruction is not register file, so which means actually it don't care. Okay. So anything is okay. So this can be connected, and therefore this path can be connected to the right data port, but it don't care. Okay. And then how about the mem write? It's also 0 because branch instruction does not access data memory. And then ALU source. So branch instruction has 2 source registers. So which means this pass and then this pass should be activated. So ALU source is the also 0. Okay. How about the reg write? Branch instruction does not update register file. Branch instruction updates program counter. So reg write is also 0. Okay. So based on the OP code, which means the category of the current instruction and control unit of the single cycle processor inside the control signal. And then based on the definition, the instruction set architecture. Okay. So which means that if we know the definition, if we know the required operations by the current instruction, then we can easily decide the control signals from control unit. Okay. I hope everyone can understand. So this is the control unit part of the single cycle processor. So okay, let's see. So actually, so So for this single cycle processor design, we start from the required steps for executing instruction. And then based on the definition, then based on the required operation for each step, we define the behavior. We define the behavior of hardware components also, and then we connect the input and output ports of the different hardware components. So which means we build data path of the single cycle processor. And then when a single cycle processor is built, then we know that the control signal, so some hardware components require control signal. So which means that this processor requires control unit based on the instruction. So control unit is required, and then the control unit generates the control signal for hardware components. Okay, then we can define the required control signal for different kind of instruction, right? So usually, and then actually the control in the single cycle process design, there are two control units, and the main control unit and then ALU control unit. And the main control unit receives the opcode field from the instruction. And then based on the definition of instruction, then we can easily generate the control signals for current instruction. Okay. And then the ALU control signal besides the final ALU operation control signal based on the function 3 or function 7 field. And then ALU OP signal. Okay. That's the control signal of a single cycle RISC-V processor. Okay. So I hope you can understand how control signals are decided by control unit. Okay. So this is the single cycle RISC-V processor. So this means that every cycle, this processor can execute a single instruction every cycle, every clock. And then, what is the issue? So in chapter 1, we learned that execution time is the instruction count, then CPI and TC, the clock period. Okay. Actually, the instruction count is determined by software and then compiler, and also instruction set architecture. So hardware cannot decide the instruction count, right? And then CPI. What is the CPI of the single cycle processor? So I explained that this single cycle processor can execute a single instruction every clock. So which means this is a clock per instruction. So which means CPI for the single cycle processor is 1, because it consumes one cycle per instruction, right? And what is the TC? It's the clock period. But if we use the single cycle processor, then performance can be low. So it is because the critical path is so long. What does that mean? So I said that these are hardware components, and then other components have delay. So which means that if a certain input signals are given to a hardware component after some delay, then outputs are generated. So which means that this instruction memory has the delay like the T1, and then register file has the delay of the T2, and then so both box and some multiplexer has also delay, right? But it's just ignore the delay of the multiplexer. And ALU has the delay like T3, and then data memory has also delay T4. And then in order to write some data to the register file, it has also delay T5. So what does that mean? Because each component, each hardware component has delays, and then in order to execute a single instruction, these delays need to be accumulated. So for example, for the instruction fetch step, we require delay at T1, and then decoding, so we also need to add the delay T2, and then for the execution like ALU, T3, and then T4, 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 and T5. This is the write back, this is the memory, and execution, instruction decoding, and instruction fetch. Then for the single cycle processor, these delays need to be accumulated. Why? I said that in a single cycle processor, this processor needs to complete executing a single instruction within clock period. So which means that these delays of hardware components beside the clock period. So clock period of the single cycle processor should be sorry. Should be greater than the accumulated delays of hardware component. So the clock period should be lower than the accumulated delay of the hardware component of the single cycle processor. So which means that PC is high. The clock period is low, is high, which means execution time is also determined by clock period. And then if the clock period is high, performance will be low. So which means if we use the single cycle processor, then the clock, we cannot reduce the clock period, and then this is the very critical for the performance of processor. Okay, this is because the delays of each hardware component will be completed and accumulated to calculate the clock period of the single cycle processor. And it's not good. It's not good for the performance. So this, with the single cycle processor, this single cycle processor can execute every instruction of RISC-V, right? So which means that if the instruction is given, then this single cycle processor can generate the defined output. That's it. It will work fine. But problem is low performance. Okay. Performance is also matters for the process of design of the computer system, as I explained. That's why we learn about the performance of a computer system in chapter 1. So single cycle processor has performance issues, and that in order to improve the performance of this single cycle processor, and then computer architects have developed pipeline processing. Okay, so we will learn about the pipeline processor class. It will be next week because we will take the midterm exam on Thursday. So, but just remember, so pipeline processors are developed for improving the performance. Okay, either because if we use the single cycle processor, we cannot reduce the clock period. I think it's very critical for the performance. Okay. Okay, so I will start here. And then, our midterm exam will cover until this slide. Okay. And then in the next class we will cover the pipelining of the processor. Okay. Any questions? 예. 뭐 사대를 어떻게 설계를 하느냐에 따라 문제가 있긴 하는데, 뭐 이렇게 하면은 문제가 될 수는 있긴 하지만, 만약 그 와이트 시그널이 좀 더 하이어 파이어로 있다고 하면 사실 문제가 없을 수도 있고, 그건 설계에 따라 달라지긴 하지만, 근데 이제 저희 코드를 시그널 만들 때 그런 케이스는 좀 생각 안 하는 것보다는 없게 하는 것이 되게 좋겠죠. 그렇지만 그렇게 유전이를 하는 사람들이 뭐 굉장히 잘할 수 있었죠. 이거는 그 데이터 메모리가 어떻게 조작하느냐에 따라 달라지는 때문에 아까 틀리다 할 수는 없죠. Okay, so thank you for attention and then see you in the next. Good luck for your presentation, right? Okay, okay, bye guys.